I'll be starting with natural language processing is one of the important aspects, uh, like machine translation and neural translation. You might have come across different uh, situations if you have already worked with an NLP. So these problems are very commonly used in solving a lot of NLP aspects, okay, NLP problems. So in this session, primarily I will be covering machine translation and seek to seek. Though machine translation with neural translation comes with seek to seek, it has another part is called attention. But I'll take that part in next session, as it is with the time constraint we will be covering only these part of machine translation and neural translation. So with that, we'll go ahead. So this is very familiar screen. If you see here, we have a Google translator, right? So where I have few Chinese characters.
Yes.
All right. So I was here. Uh, so we can see here when we, I mean, it's a most advanced uh, translation system that has been developed by Google. We have seen our probably if anybody has used um, you know the Google Translator, and there are a few more which we'll talk about in the next slides. So in the earlier times, right, in 1939 when it was developed with machine translation, we need to have a lot of computation power, and probably uh, you know punch cards has to be coded with these translation techniques. So it was really complex, and so it is now. Though deep learning helped a lot in improving on this area, however, it's a very important aspect that we should be understanding. There is a lot of improvements required, and in recent times as well. So with that, if you see here, Chinese sentence is easily getting translated to the desired language, right? Whatever language we chose it to be translated. Uh, so if you see, machine translation systems are converting text from one language to text in another language. One such example systems is Google Translation System. So there are many other translation systems, but not so popular or probably not so successful. But these and one more is there, being they are very uh, popular and they are doing good with this area. Okay, so with that note, let's start on this. So a history of machine translation from the Cold War to deep learning, right? So this is a very generic timeline which shows in 1950s when rule-based machine translations were very kind of very much used due to Cold War between USA, Russia, and other countries, right? So USA kind of took it as a challenge of translating Russian language into English, right? So that was a direct machine translation, and mostly transfer based, and they used rule based techniques to translate them. So after that, example based machine translation came into picture, and you see here, then the statistical machine translation came, and then came neural machine translation in 2015. So it's a long time, and it's a huge gap between all those time areas, right? So from 1950s to 2015, and now we are at 2020, right? So what do we see next? In that's what we'll be looking at. Uh, so in these 20 years, there from 2015 or around 2010 to 2020, when Google has first published their Google Translator. Um, so from that time to current times, we have a huge improvement in this area, which we couldn't do in this phase of time. So within 1950s to almost 2010. So we have covered almost 20 to 30 years in very less time. I mean, the improvement due to the advancement of deep learning. Okay, so that's the um, interesting part, right, of these areas. So let's move ahead with this. I'll quickly check if there are any questions. Okay, so this is a news that came in 1950s. A girl who didn't understand a word of language of Soviets punched out the Russian message on IBM cards. Right, the brain dashed off in its English translation on an automatic printer at the breakneck speed of 2.5 lines per second, reported the IBM press release. So this was a great news at that time, and it was really revolutionary in terms of machine translation, right? I mean, translating complete language into the desired language. I mean, that time it was French or probably mostly Russian language to English version. Although there were a lot of things that has not been written in the news or not publicly known. So those things like using pre built translation or pre-built grammar faded into the system that helped it to perform well. And also there are so many other feature engineering work that has to be done before getting it done, right? So those things are hidden, though this is very important to know that we have achieved these things in 50s, in 1950s, right? So systems were mostly rule based at that time, and using a bilingual dictionary to map Russian words to their English counterparts were used. So if you see, this is a very nice picture that I got from a Russian blogger, where is talking about Russian English dictionary being used for that, an endless list of rules about translation, word matching, and harmonization, and the rest, right? So this is a kind of dead linguistics, so they they have no job. So after that, spell check there were a lot of work has to be done, though this is done by the machine, right? So spell check and translation and make everything great again. So that was the challenge with which IBM had a lot of advancement in this area, right? So with that, so we'll go ahead with statistical machine translation. So that was kind of a brief history of machine translation, and there are so many techniques or ways or research has been done in that area. And later comes SMT, which we call statistical machine translation, which also has different types of machine translation, different types of variations of machine translation. So we'll not go very in depth with each area, though it is not important as although uh, this is to note that in this area we have really done well till 2016, because all of the Google translation or other translation based systems were using SMT for translating from any language to other languages, right? So that was a very well timed with SMT. So in early 1990s, right, at IBM Research Center, machine translation system was first shown, which knew nothing about rules and linguistics as a whole. And so it doesn't need to know linguistics, it doesn't need to know any rules as such, right? You don't need to have too much of expertise to translate. And it analyzed similar text in two languages and tried to understand the pattern. So the difference is parallel corpus. So we used parallel corpus in SMT to translate from one language to other, right? So that was a very different approach than normal machine translation, right? So if you see here a particular there are some paragraphs which are feeded in a similar fashion for both the corpus. So corpus are basically a document, right? So you feed in multiple documents with a parallel nature, so that helps in translating the language. So we'll see more about this, but there are again different techniques of getting parallel sentences. But this is how it is done. Basically, this is the nature of the model. Okay. So with SMT, the idea was simple yet beautiful, right? So an identical sentence in two languages split into words, which were matched afterwards. So this operation repeated about 500 million times to count. For example, how many times the word dash house translated as house versus building versus construction, right? And so on. So this way we kind of achieved this without doing a lot of rule based or linguistic based uh, uh, pre-processing for translating the languages, right? So the method was much more efficient and accurate than all the previous ones, and no linguistics were needed. The more text we use, the better translations we got. So that was a very great achievement with statistical machine translation, or SMT. So if you see here, there is a sentence which is sorry, so which is in French, right? So we are translating this does house and blows house and does auto. So that goes to with different weightage to these, and it basically relates to the particular word that is parallel to it. So that's why we call them parallel corpus, right? So this is, let's say, C1 and C2. So we see the match between them, and then we get the translation from that. Okay. So, what was behind it? I mean, what exactly does this? Let's go a little more in depth. I'll give you a few seconds to think over. So, as we see here, the core idea was a learned probabilistic model from data, right? So, suppose uh, this is basically a Bayes theorem where something is given and you have to predict something. So y given x, right? So a sentence, let's say uh, a English sentence y given a French sentence, right? So we need to predict the English sentence given a French sentence, or we need to predict the English sentence given a Chinese sentence, right? So the probability uh, of each word in a sentence, that's what we we solve within using this statistical machine translation. Primarily that's the purpose. So we want to find best English sentences y given French sentences, let's say. So we find the argmax of py x, right? Y given x. So we use Bayes rule to break this down into two components further to be learned separately. So one thing is translation model, and another thing is the language model. So translation model is p of x given y, and p of y is separate, and that's what we call as a language model, right? So the language model is, let's say, my targeted language, right? So my target is my language model, and the source is my translation model, right? So here French or whichever language we are uh, uh, targeting, so that would be my the French sentence is my basically the source here, and the English sentence is y. So that's my target sentence, right? So I am feeding in a French sentence and I want to get English sentence, right? So mostly this is how the statistical machine translation been done at that time. So if you see Brown et al. In 90s, there was a famous paper for SMT, and which got popular, and primarily it is using the argmax of a normal probability over sentence. So a English sentence. So I'm just repeating this because it's very important to understand uh, as we do the similar thing in neural machine translation as well in recent times. So it's very important to understand that we get the probability of y given x. So a sentence is given. Based on that, we will be uh, predicting the next sentence, right, or the next word for translation. Okay. So there are two parts, right? As I talked about the language model and the translation model, right? So the components p, y, and p of x given y in the equation above are referred to as the language model of the target language, right? And the translation model respectively. So that's what we said, right? So these are the two components. So the argmax operation over all sentences in the target language denotes the search problem and is referred to as decoder. So that's what we call it as a decoder in this in these type of techniques, let's say statistical machine translation. So there is a decoder uh, here as well, which we now came up with the deep learning model with encoder decoder architecture. So that's what kind of similar thing that we have done before as well in SMT. So given a target string y and of length m and consisting of words y1, y2, ym, let's say, we can write the language model probability py as, right? So probability of uh, y, right? So probability of y would be probability of y1, y2, and so on. The number of words consisting of in that particular string or the sentence. So we get the sum of all the probabilities, and we find the total probability of the 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 given the output of the given sentence, right? So this converts the language modeling problem into one that requires computing probabilities for a word given its history. So it was very now let's say there is a y at a given text, right? So I need to have the probability of the history of this word. Let's say I minus 1, I have yi plus 1. So a word here, a word here, and a word here, right? So we need to get the probability of the history of these words as well. So that was kind of a requirement with language models, and considering the statistical machine translation. So primarily, though, we are finding the probabilities. On top of that, we needed the probability of the history, I mean, given history of the word, right? So that became also an important aspect in finding the next predictable sentence, predictable word from a given sentence, right? Okay. So the decoder performs the actual translation here. As you see, that the decoder that we were talking about as a language model, given a sentence X, right, sentence X, it searches for a sentence Y in the target language with the highest probability P of Y given X. So we see here the decoder has the input of a of the English language and the input of source text and the translation model, right? The target is the French sentence or the target language model that also will be fed into the decoder, and that will give us the translated word in French, right? So decoder is primarily the language model that we call, right? So given a sentence X, it searches for a sentence Y in the target language with highest probability P of Y given X, right? So anything which has the highest probability will be taken further for as an output to the translated words, right? So with SMT, there is another thing that came into picture is alignment. So how to learn translation model from the parallel corpus uh, P of X given Y. So I'm uh, still talking about the same concept, and to go deeper into SMT and the technique that is used, and it's a very basic mathematics that has been used, and it's very important to understand here. So we can break it down further and introduce the latent a variable into the model. So earlier we had something that, let's say, p of x given y, and then we had p of x, and now we have introduced p of x, a latent variable a, along with the sentence that to be predicted, right? So where a is the alignment, and that is the word level correspondence between source sentence x and the target sentence y, right? So that's what the a does here. So it finds the alignment between the two parallel sentences, right? So as probably when I was talking about earlier the parallel corpus, right? How the parallel corpus works. So they should have an alignment concept, right? So this is where a plays a role. Okay, so let's go ahead. So what is alignment again? Alignment is the correspondence between particular words in the translated sentence pair. So its typological differences between the languages lead to complicated alignments. So some words have no counterparts. So let's say I might have a Japanese sentence where I do not get, for each word I do not get a corresponding word in the parallel corpus, right? So I can have something, let's say a word one, word two, word three, word four, and this is my given sentence, right? Source, and I want to get something in English, so I might have multiple relations with a single word, or I might I might have an opposite, right? So this is kind of a relation with one to one to many, and many to one. So all things can be uh, uh, be there between these parallel sentences. So it sometimes it becomes very complex. However, it was very important to find the alignment with the SMT or parallel corpus techniques where we are trying to translate. So if you see here in this example, the balance was the territory of the Aboriginal people, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different words, and in this side I have 1, 2, 3, 4, 5 words, right? So if we match them in, uh, so Japanese, I think la is da, and the balance, let's say, gets combined with this, and for was da, and territory, it is the same, apartment, patent, right? So, and for off and the will be this. Okay, and for Aboriginal and people will be right. So it's a many to one relationship, and there could be different types of alignments with these given sentences. Okay, so here is a question here: how do we ensure we have chosen best translator? So I will come to that. How do we choose best translator? So basically here the translator, you mean probably the techniques that is used, right? So SMT is an area, or machine translation is an other area. Again, I will come to neural machine translation, where we have different algorithms that is being used, right? So with SMT, we have word-based, phrase-based techniques. In word-based, again, we have 10 different models. Probably we cannot go through all the models. So it all of them has a different advantage, over the other. But however, it is kind of uh, completely dependent on what sentence that we are translating, though there is a lot of improvement over time, and the accuracy and the time for training has improved a lot over the corpus. So uh, obviously we can make more logical decision to choose which translator to be used, but it is again not totally uh, fair that we can say that SMT systems were not at all well, right? Because till 2016 we are using a lot of SMT for solving the language translation problems. So another question here is, so alignment is the key and learned through training. That's right. So alignment is uh, the learning between the sentences. Let's say I have many to one relation, or with a word, or one to many, or many to many, right? So these understanding, or the information or the feature has to be there, right? So that is uh, captured through the alignment between the two parallel sentences. Okay. So it still remains a question um, till now, that how do we improve, or what would be the best translation model, right? So we need to work on that, do more research, and there would be always a scope to improve in that area, because this is one of the aspects of natural language processing where translating human language is really complex, and we have so many languages over in the world, right? So if we consider um, Google Translator we have nowadays, it detects at least all the languages that we type in. Sometimes it doesn't do that. Sometimes it gives us very junk output for a given sentence. So those things still needs to be improved. There are a lot of improvement areas in terms of the accuracy and the way it is responding. Let's say sometimes it gets biased to a particular type of language. So those problems are still has to be resolved. So though it is very important to understand the history and how empty or SMT based systems were performing well, and there are so many new techniques has been developed with advancement of RNN LSTM, by LSTM, and different bidirectional algorithms in deep learning area. Those helped a lot in improving in this language translation, as we don't need to do manual feature engineering. The most complex part has been taken care by the neural network. So that was the feature engineering that humans has to do, right? So to find out, let's say here, the alignment and their grammar, their translation, there are a lot of other things that comes with when we do translation. So that was the complex part that is taken care by the deep learning. So if as a whole, if you see in MT, we I mean in the machine translation we used a rule based technique where we have to give each and every word to be detected with a certain rule or certain technique, and you need to use linguistic methods to be punched in punch cards. And later SMT came into picture where we don't need to do rule based things, we don't need to provide any rules, or just we need to tell that these words occurs these many times. So probably if a house means house, so that means it is more probability is there to be it is a house in English word, right, sentence. So that way we kind of reduced the feature engineering work, but still there were so many other things that has to be done with feature engineering part in SMT. Okay, so with that we'll move ahead. So as I was talking about, there is a word-based SMT, the bag of words model, where we have a word given to with a parallel corpus, but we basically chose I mean a different word from a sentence, and we feed into the system, and we get the alignment for each of the word, and then we get the probabilities of those words and find the translated words. So there were again a lot of other things that comes into picture where probably I might have a different type of value, or probably similar meaning that contains I meaning of I in the other language, that the target language, right? So these things also cannot be ignored, and along with that there could be some spaces that, or probably a quotes or something that has to be ignored by the system. So we introduce letter null or something that can be related to these kind of anomalies that comes or basically the different words that comes into a sentence. So with word-based SMT, again, there was another model, and there are 10, 12 different models with word-based SMT. We cannot discuss all of them, but just to understand that all of these are basically improved over other, but however, they are not still very good in doing the translations. So this is also again the similar way that we are matching the words with the parallel corpus, and we have introduced something a word under order in a sentence, and then we kind of mapping them to the target sentence, right? So later phrase-based SMT came into picture, which really had done a lot of improvement in this area. And this method is based on all the word-based translation principles, like statistics, reordering, lexical hacks. So it has, although for the learning, it splits the text not only into words but also phrases. And these were the n-grams, to be precise, which were a continuous sequence of n words in a row, right? So we might have heard about the n-grams, where unigram or bigram or trigrams are used to understand the word based, and also the ordering and the lexicography of words. So we kind of have done everything in terms of understanding the word, feature engineering, a bit, and then taking each word and then taking a phrase by phrase and taking probably n-gram, like 2 words, 3 words, 4 words, like that. So we kind of get all the uh, mm, uh, possible meanings or features from a sentence, right? So I would not say context or meaning of the sentence. I mean here, like, we got the necessary features to translate to a different language, right? So the probability is to calculate the probability, we have more information now, right, with phrase-based SMT system. So though it was very popular over time, and besides improving accuracy, the phrase-based translation provided more options in choosing the bilingual text for learning. And for the word-based translation, the exact match of the sources was critical, which excluded any literacy or free translation. The phrase-based translation had no problem learning from them. So we had a lot of improvements over word-based translation, and the exact match of the sources was critical, which what it did is excluded any literacy or free translation. Okay, so total superiority of permissions, that is one of these word-based translations, and uh, they were good, but not so good. And then we had a phrase-based translation where it takes the context of neighboring words, right? So we get the feature with along with its context, like what it means or what it is talking about, which we did not have in word-based translation. Okay, so this is kind of, there are again a lot of variations with SMT. We had I mean, there are till 2016, or probably till now, there are many organizations who prefers SMT, but they who are not using deep learning systems, so they have still been happy with SMT systems. So starting in 2006, everyone began to use this approach, and Google Translate, Yandex, and Bing. So Yandex, I was thinking about. So I was telling at the beginning. So one of the translator systems that is recently being more popular, and you can probably go to Yandex site and check for different languages, how does it translate and what does it do good in comparison to Google Translator. You'll get a better idea of what to be improved and what not actually being done good by the other system. And so they were using SMT, and other high profile online translator worked as a phrase based right up until 2016. So moments when Google either translated the sentence flawlessly, or we might have remembered those times when we put some sentence from other language, and you expect it to be this, but it shows you something else. Or probably sometimes you expected this and it really did very well, right? So those were the very very surprising things with the Google Translator when it came at the early stages. So in 2010, there was a video by Google that how do they do the translation. So we'll have a quick
look into that in few slides. But just to understand, so Google either translated the sentences flawlessly or resulted in complete nonsense. So this is kind of still, I mean, right now it has been improved a lot, and there we do not see nonsense translation, but we still see noise, and we still see biasness with different languages, or probably few languages could not do well with the translation. So phrase-based translation has become so popular, as we were talking about on the SMT. So in SMT, phrase-based were very popular, and that's when we hear statistical machine translation. That is what is actually meant up, right? So we kind of now whenever we talk about language translation, we think about SMT systems with phrase-based machine translation. And but till 2016, where kind of Google has launched a different system. They announced a new technique, so that kind of revolutionized with the complete aspect of language translation, right? So we'll talk about that in neural translation, and how that has changed the complete structure or the way we translate the sentences. So with that, we'll move ahead. So conclusions with statistical machine translation. So back then, no one even thought that Google was already stoking its fires, getting ready to change our whole image of machine translation, isn't it? And SMT was a huge research field, and that time, and the best systems were extremely complex, hundreds of important details we haven't mentioned here with SMT, as I've spoken about earlier. And systems had many separately designed subcomponents, lots of feature engineering, and needs to design features to capture particular language phenomena, require compiling and maintaining extra resources like tables of equivalent phrases. So these were extra tasks that needs to be done with SMT, and a lot of human effort to maintain basically repeated effort for each language pair. So that was kind of a challenging task with SMT, and still being used for a few areas, though it has shortcomings with a few things. Okay, so with that, we'll move ahead with the neural machine translation. Okay, so neural machine translation. So how exactly does it work? Does it work so well, or does it work so badly? We don't know. So a video that was released in 2010, and I like this video, is very good at explaining. I mean, Google always been good in this area, and how they have been improved over time. We can see with this neural translation model. So there is a question which says Google use translation. Google use which translation currently? So of course it uses deep learning techniques. There is no question. But in deep learning we have a different algorithm, right? So um, it can use nowadays BERT, so which is very well and good in translating your sentences. There are a lot of other custom built models, like with RNN, which is the base of language translation, because we get the context, we get the timestamp of the previous word from a given sentence. So where with that we have advancement on LSTM and bidirectional LSTM. So it is completely customizable, and how we wanted to do that. On top of that, we use attention nowadays, which really give a lot of improvement over these. But however, they are not completely perfect, and there is still a lot of improvement that has to be done, whatever we see with Google Translator nowadays. Okay, so let's have a quick um, show of this video, and that will refresh you and kind of uh, give you more energy of understanding these complete translation techniques. So I'll play it. It's a 2 minutes video.
Yeah, hi Indrajit. Is there supposed to be audio?
Sure, if the audio is playing.
No, audio is not playing.
All right. Uh, there is the audio, but
I guess you can remove your headset. That might trigger the audio for rest of us.
Let me do that. Thanks.
Yeah, no audio, but that's okay. Let it be.
okay. So that was the video. I'm sorry, the audio is not available. However, I mean, you might have seen the translator script. So this is basically a demonstration of how Google Translation, Google Translator worked at that time. So it was in 2010. So as I have mentioned, in 2016 they have changed, and they have come up with a different announcement. So I'll come to that. So okay. So a quite amusing paper on using neural networks in machine translation was published in 2014, and internet didn't notice, but 2 years later, in November 2016, Google made a game-changing announcement. So this happens a lot over deep learning deep learning area, that we tend to give less importance to some of the papers that came into came into 2 3 years back probably, and that doesn't give any popularity, and probably nobody is kind of talking about it. But these big companies like Google or Facebook, and they come up with some new kind of technique which are basically based on those papers, uh, which really surprises everyone, and how they utilize this knowledge and the research of these areas. So Google came up in 2016 with a different announcement, and where they talk about a neural network for machine translation at production scale. So they say, like, I just took this few lines from here from their blog, which I can see still been published. So 10 years ago, we announced the launch of Google Translate together with the use of phrase-based machine translation as the key algorithm behind this service. Since then, rapid advances in machine intelligence have improved our speech recognition and image recognition capabilities, but improving machine translation remains a challenging goal. So that they have said in 2016, and in current times, although there are improvements, but still it is a challenging area, there is no doubt. Okay, so that's a interesting milestone that has been achieved in 2016. And as we see the history of machine translation and statistical machine translation over time. So let's go deeper into this neural machine translation. So you might have remembered the Prisma app, right? So where I mean, few years back, I mean, probably last year, it has become so much popular for all the users, and everyone is using Prisma for checking how they look, or they become older, when how they will be looking. So this is basically a style transfer concept from deep learning in vision, and the text would be that precise artist style, and we would try to transfer it while keeping the essence of image, or in other words, the same essence of text. So let's say we wanted to kind of do the same thing as we do for the image. So this is kind of these style transfer is basically we chose to take a certain training features, and we stop the training at the time, or probably we do not take those training samples which are already completed, and at certain stage that we take the training output, and that shows like an painting of some artist. So let's say if we do the same kind of thing with the text, would that be precise, like will it look like an artistic or linguistic translation? So let's understand that. So like we can transfer the style to a photo. So can we do that for a text? That's the question. So image, let's say we are imagining trying to describe a dog, right? Average size, sharp nose, and short tail, always barks. So if we have these set of dog features, and if the description was precise, anyone could draw it, even though like let's say if you might never have seen it. So about any picture or any person, we can have a bit of idea, and we can kind of derive that image or picture of that person. So like here, big ears, short paws, and wide breast, and small tail. So these are the features of the dog that talking about, right? So that same thing, what does features mean in terms of text, or in terms of um, textual data? So we will see that further. So one neural network can only encode the sentence to the specific set of features, and another one can only decode them back to the text. Both have no idea about each other, and each of them knows only its own language. So it's kind of a story, right? So I'm talking to you uh, uh, with you know, with certain features or certain um, kind of certain numbers, right? So I'm telling you some numbers, and you don't know about what I'm talking about. So I'm talking about probably about some person, and you are probably trying to understand some numbers. So based on these numbers, you are telling me, okay, this is what it is, or these are the lines, that this is the translated sentence, right? So that's kind of a very good depiction of how the encoder decoder behaves. So right. So there is a question number it is mentioned is Unicode. I'll come to that. Just a depiction of these. So these are basically vectors from like, if you know word vectors and globe, how neural network does is we get the vectors from a given sentence, and we basically we break them into different words and get each word vector, and we get the probability of that, and those probabilities are basically comprising the vector, right? So in encoder decoder, if you know, we do a dot product of the encoder and decoder output, and then we apply softmax on top of it, and then we do attention or whatever we needed, right? So that's how normally this is done. Okay. So questions, right? How do we find those features, and how to deal with the text? Another thing is like, what type of neural network should be used for encoding and decoding, and which type of neural network architecture? So these kind of questions definitely comes in mind when we think about translating a sentence using neural network, right? So how do we find those features? uh, we don't need to find features literally in natural language, in neural translation, um, because a deep learning network kind of takes care of it mostly with the features that comes in from a sentence. So what type of neural network should be used for encoding and decoding? So that's our uh, decision that we make based on what we are translating, and uh, and how much advantage they have over other models, right? That is an intuitive decision that we need to make. But however, we can always learn about the best models so far in the market, and the best neural models which are really doing good in production, like Google has set an example, Bing has set an example, right? So these we can always take as an example, and probably you can work on this further for improving these areas, right? There is no way to be get better on these aspects with deep learning and neural network. So which type of neural network architecture we choose? So the decision is again based on, as I told you, probably you can go with the popular model, but that will not give you good accuracy, or probably you may go with a model which will give you good accuracy but not so fast. So these decisions are completely based on your experience, and I would not say trial and error, but more of an intuitive decision based on how these works and the understanding, your understanding of the network, right? So that's very important here. So what is neural machine translation? So a neural machine translation is a way to machine translation with single neural network, and the neural network architecture is called sequence to sequence. I mean, I have taken a paper example from 2014, which is very popular in seq to seq, and there were a lot of other variations of it, like character to sequence, character to char. So these are different variations of RNN, I can say, but still the most popular and um, kind of doing very well in this area is seq to seq models. You might have heard, and we'll talk about that in the next slides. So neural machine translation is a way to do machine translation with a single neural network. So we use a single neural network to do the machine translation in neural machine NMT basically, right? So how does it look like? So if you see here, sequence to sequence model, we'll spend a little more time here in understanding this. So let's say earlier we had in SMT we had a parallel sentence. We did a lot of feature engineering, and then we got this alignment for the sentences, and then we improved the sentence alignment, and then we do phrase-based SMT. All of these are not that. What we have an input sentence. Let's say source sentence in the language that the language that you wanted to translate to, right? That will be given as an input to the encoder. What is an encoder? So encoder is basically formation of network layers, neural network layers, right? Formation of network layers, and they are kind of, say, H1, H2, H3, right? And I have certain inputs to that. So normally this is how it looks like. So what kind of neural network? We use RNN here, right? So RNN takes the input from the previous layer to the next layer, and it predicts the output of it, right? So let's say here I use a decoder. So if I take one RNN like this, and I have same another RNN like the similar kind of network, so I will call this as encoder, I will call this as a decoder. Okay, so that's how this is kind of understood. What we want is the dot product of these two. So these two, the dot product of these two we get as an output, right? So where decoder is basically a condition based probability. So decoder gives us a way to put the condition, like we had in a Bayes theorem, probability of x given y. So when we have a condition probability applied, let's say, then we can talk about the decoder. We are also there. Also, we have the decoder concept, but we did not use neural network. Now we are using neural network here, and we call it specifically. We are using RNN here, and let's say I have a sentence input. It am enter, right? So it goes as an input to this RNNs, and the output gets fed into the decoder. Let's say it has a start and a end point, right? So encoding of the source sentence provides initial hidden state for the decoder RNN, right? So this encoder, so as we understand clearly, this encoder is basically the RNN layers, right? Okay, so then I have a decoder model. So in decoder also we will use another RNN. Now let's say it starts at a certain point. It's not that so it starts with a certain point and goes as an input to the layer, and then it gives it applies argmax on top of that, and we get the probability of the highest probability of a sentence that gets as an output. So then again he goes as an input. So this is at the training time of this is not at the training. So let's say this is just at the time of you do testing with the network. So you create the network. So that time you feed in key and then it comes as an hit, and then for again as an input hit here. So we get the output for that particular word. So for each word we get a similar kind of input with the, if you see the pink arrows, basically getting the input to the next layer, right? So this is how we kind of get the input and then predict the output of that, and then we get a total target sentence output. So decoder RNN is a language model again here, like we talked about it earlier with p of x given y and p of y. So this is my language model, right? We call it as a decoder or the language model. Okay, so encoder RNN produces an encoding of the source sentence. Decoder RNN produces a decoding of the of the of the target sentence, right? So this diagram shows test time behavior decoder output is fed in as a next steps input. So that's how this complete model works, and it's basically a seek to seek model that we call it seek to seek. You can have a look into the seek to seek model paper that has more explanation, more maths on what has been done behind it. So normally this is what the uh, what it is actually on in a top layer we can explain. Okay, so a sequence to sequence is useful for more than just machine translation, and many NLP tasks can be phrased as sequence to sequence. We have a lot of applications with seek to seek models, like summarization. We call it like say text summarization, where we have a long sentence and we want to predict the short text from them. We have dialogue generation, like previous utterances, and then we wanted to predict the next utterances of that. We have parsing, like we have certain input text and we want to output parts as a sequence. Again, something like a code generation, right, where you give a natural language and it gives you a Python code, right? Very interesting problems are being solved using seek to seek models, and they are kind of uh, different in each. I mean, the use cases are different, and the way we train them and the way we form the network layers are different. So this is kind of where we do a little more uh, work on ourselves to form our own kind of network. I mean, you cannot do a lot of changes. However, uh, the hyperparameters, right, number of hidden layers, number of uh, neural networks, so these things you have to decide based on what kind of output you are trying to achieve. Okay. So, neural machine translation, the seek-to-seek model is an example of a conditioned language model, right? As I was talking about the conditioned probability. So, language model because the decoder is predicting the next word of the target sentence Y, and conditional because it's predicting its predictions are also conditioned on the source sentence X, right? So NMT directly calculates P of Y given X, where P of Y1 given X, and let's say P of Y1, right? So Y1 is the first word here, and then the next word Y1 I will take W2, right? So here, I mean, as I say as an example, so let's say in the first, I will calculate the probability, I'll concatenate them. The probability of Y1 and given X, the sentence, plus the, and basically a dot product of, so probability of Y1 along with, I will take So probability of y2 along with I will take the y1 also, which I already did the prediction. Along with that, again in the next probability of y3, y1, y2 given, and then so on, right? Probability of yt of y1, y2, and yt minus 1 given, right? So this is how we do the calculation, and the probability of next target word and next target word given the target word so far and source sentence back. So we are taking care of the history and we are taking care of what would be predicted next, right? Is it clear? So this is where we make the condition probability very useful to this technique. So how to train a neural machine translation system? So answer is they get a big parallel corpus, right? So training is one of the biggest aspect or challenges of neural network. So you don't need to do feature engineering, you are happy, but let's say how the output should be, I mean how it has to be trained, that is something is very important aspect in any neural network the training. Okay, so any kind of training that we do, we need to take care of the feature engine, we need to take care about how those has to be trained, the number of layers and parameters and epochs, everything, right? Okay, so training a neural machine translation system. So I have an encoder, and the best thing about these translations, I mean the neural networks, is like in SIG to SIG is optimized as a single system with propagation operates end to end. So we have a complete back propagation I mean applied from the encoder to the decoder, back through decoder to the encoder. So this is kind of a very advantageous. And how, what does back propagation does? So we find the loss, right? We find the loss of let's say a given sentence and the predicted sentence, right? So what would be the loss between them? That's what we are trying to find with j1, j2, j3 here, right? So let's say from the network, the source sentence, it's coming in the sentence, the words for the given, right, source sentence, and we are predicting the next word for a given word. So how much loss we are getting, so that we get from the given sentence, right? So with the output sentence. So the training is basically we do we calculate the j, right? We calculate the loss for a particular output with a given input. So we find that basically a negative loss or negative log entropy of the word. So you see here the word he, right? So that has a negative log probability of he j1, and negative log probability of with is again j4, negative log probability of end is j7, right? So we concatenate them, basically add them, and then we find the total loss in the system, and right. So that's what we do in the decoder. And once that is done, right, so we apply a different decoding algorithm to find the output again, right? So we saw how to generate the decoder and then target sentence by taking argmax, right, on each step of the decoder. So we apply the argmax for each step, each word that's coming in from the previous layer. So this is a greedy decoding and take most probable word on each step. But there are problems with this. There are problems with how they are actually getting us an output from a given word, right? What are those problems? Let's discuss them quickly. So greedy decoding has no way to undo decisions, right? Just understand, there is a sentence, there is a sentence where I am feeding in a something like this, and he hit me with a pie. That's what the output should be. And then he goes in, and then he hit goes in, and they goes in, and no going back, right? We cannot go back from here. With the greedy decoding, that is one of the problem that decoder faces. So greedy search will always consider only one best alternative out of all, whichever has the probability, highest probability, will get only that alternative, will not choose anything else. It will know it is not going to fix it, right? So greedy decoding has this problem. So how to fix this? We should find a way to fix this problem, because this is kind of making it very biased, or probably very general in nature for every sentence, every type of language that we are feeding into the network. So we can use the exhaustive search decoding. We could try computing all possible sequences of y, or probably this means that on each step t of the decoder we are tracking vt possible partial translations, right? So each step of t, let's say, we are tracking vt possible partial translations, where v is a vocabulary size. So this is going to be a very highly complexity. I mean, the complexity of these algorithms would be too high and too expensive that it cannot be used. So that's why it's called exhaustive search decoding. So that cannot be done. I mean, we cannot kind of try computing all the possible sequences of y, isn't it? So what is the other solution? Is to our greedy decoding is beam search decoding. So this algorithm is kind of being used with a lot of natural language generation techniques nowadays, and it's well over other algorithms. However, there are multiple other algorithms which are also helping to fix this problem, but we'll talk about beam search decoding on this session. Okay, let's go over it. So what we do in beam search: on each step of decoder, we keep track of the k most probable partial translations, so which we call hypothesis, right? On each step of decoder, we keep track of the k most probable partial translations, which we call hypothesis. Let's say k is the beam size, right? In practice, around 5 to 10. So my beam size will be, let's say, my beam size will, I will decide between 5 to 10. I can decide, I mean, it says around 5 to 10. I can have less as well. So this is my beam size, right? The hypothesis has a score, which is its log probabilities. So we will get the log of the probabilities, right? Y1 given yt, y1 to yt given x, given a target center. So the score will be based on that. So scores are all negative, and higher score is better. So the more score we get, the more better it gets. We search for high scoring hypothesis and tracking top k on each step. So let's say I get a value for 5Ks, and my top k is this, right? Again, I have something in the next layer. My top k is this, right? Again, in here, and my top k is this. So my path will be, this is my, let's say, layer 1, layer 2, layer 3. My path will be like this. I will choose these words to form my complete sentence, right? This is what it is showing, the log probability of the given word. So scores are all negative, and higher score is better. We search for high scoring hypothesis, tracking top k on each step. Beam search is not guaranteed to find optimal solution. However, though we are talking about beam search, this is not something that will give us optimal solution, but still we are kind of taking this over other search types or other decoding techniques, but much more efficient than exhaustive search. That's the reason we have more advantage over beam search over other search techniques, right? We don't want to use a lot of resources, time for doing the search. So how does it look like? I mean, normally this is just I have taken from somewhere, and you see here it's a visiting these and are three most likely words to start the sentence, right? So it's a vocabulary length, right? So if we are using exhaustive search, it will be the size of the vocabulary, right? So which is kind of getting bigger and bigger, right? Because in encoder decoder, when we do multiplication, when we do dot product, we generates a vector, right? And we take the arguments on top of that. On that vector, again we apply softmax or any function that we need, right? So using all of these words, have x1 x1 as an input here, x till xn. These are my beams. So b is equal to 3 here, right? These are my beams, and this is an encoder decoder neural network architecture. So whichever I am passing in p of y1 given x1 x2 xn, right? So whichever will have high probability will feed into the next, that will go to my next layer out of end these visiting, let's say. So y1 will be the output for that. Again I am visiting going in this, most likely words are to be followed like x1 xn and y1, right? So we will see a more example on this. Let's say I am, right, it's coming in like this, and then y1 as an am is coming out of from here, right? So we get a y1 y2 given x1 x2 xn equals to y1 given x1 x2 xn into y2 given x1 x2 xn. This is what we do in a beam search. Let's break this into small pieces, then we get more idea of it. So beam search, let's say I have a beam size of k is equal to 2, right? And we'll take the blue numbers. So it starts with he and I. So I get the score as 0.7 for he and for I 0.9, and this is minus, right? So of these K2 hypotheses, just keep K with highest scores. So I will take that one which has the highest score. So I will have similarly in hit and struck. In the next, let's say, set of vocabularies, I will have hit and struck, and that I will take the one which has the highest probability. Let's say hit I will take for the highest probability. So it becomes, let's say, and with a negative log, right? So we'll minus that. So we will get minus 2.8, let's say, for hit, right? And for me I will get minus 2.5 here, like as hit is chosen because that has the more probability, right? Minus 1.7 over minus 2.9, and again 1.6 over minus 1.8. So right, so we'll get the was as a from here, right? So now as hit comes from these a and me, out of these two, again because my beam search is 2, I am taking each step 2 words. So 2.8 and negative log of that minus 1.7. The previous one we will, the previous number whatever we get, we will minus from it, right? So as right a of start greater than of he or hit, right? So we and plus the plus 1 point minus 1.7, right? So we do this minus from the previous one, and here also we do the minus of from the previous one, right? So we get the next word based on that. So for each of the k hypothesis, find top k next words and calculate score. So we get the score like this, and then we get a sentence from that. So what is the sentence? He hit me with a 5. So this is where the we only take the highest scores from them, right? And 3.7, and here minus 4.3, right? We see all the scores. This is the highest probability score. So beam search is one way good, but compared to uh, compared to greedy search or greedy decoding or exhaustive decoding, beam search is far better than that. So you can do more research on these aspect, probably search with the papers with beam search and get to know how what advantages that has over other algorithms, and if there are new algorithms which came in which probably claims to be do better in comparison to beam search, right? So those things you can do as an homework and understand this particular technique. Probably you can improve your neural network based on these search decoding techniques with a different approach. Okay. So advantages of neural machine translation. What are the advantages? So compared to statistical machine translation, NMT has many advantages like better performance, right? It has better performance, more fluent, better use of context, and better use of phrase similarities. A single neural network to be optimized end-to-end, no subcomponents to be individually optimized. Requires much less human engineering effort, no feature engineering, same method for all language pairs. That is one of the biggest advantage with neural network machine translation, is that you can use the same method for all language pairs, right? And no feature engineering has to be done. So this is kind of a very advantageous with any deep neural network. Okay. So disadvantages compared to statistical machine translation, NMT is less interpretable, right? As we see for all the deep neural networks, we can say it is dark. I mean, we cannot basically see or what's happening. We cannot control what's happening inside. So that kind of a bit disadvantageous over how we had done it in SMT. For each feature, each step, we can modify, we can improve, we can probably build a new kind of techniques to improve over the previous technique. Like word from word based to even to phrase based. Probably in future we can do graph based or something like that, right? So those things are always there in comparison to the other. Okay. So NMT is difficult to control. For example, can't easily specify rules or guidelines for translation, and safety concerns are also one of the disadvantages with neural machine translation. Okay. So what are the evaluation criteria for neural machine translation? The first and foremost thing that comes in is bilingual evaluation under study, right? So Blue compares the machine written translation to one or several human written translation and computes a similarity score based on n-gram precision, usually for 1, 2, 3, and 4 grams, plus a penalty for 2 short system translations. But Blue is not useful or perfect. There are many valid ways to translate a sentence. So a good translation can get a poor, bilingual evaluation under study score because it has a low n-gram overlap with the human translation. So these kind of challenges are always there in the evaluation criteria, evaluation criteria, right? So these we have to also take a little measure on. So you might need to find a better way to evaluate uh, your neural network. So with machine translation progress over time, we see that phrase-based SMT and syntax-based SMT and neural machine translation. So we see the neural network is doing good. Over is you see the red uh, bar here, right? In over 2016, although I don't have the data for 2020, though we can you can search that how much better neural network is doing. I mean, we can basically do experiment now. We have the algorithm, we have the code, everything ready in our hand. We can test it out and see how better it is doing over MT and SMT. However, one more information I kind of would like to mention, the syntax-based or SMTs are also were kind of very popular and doing very well in statistical machine translation area. Okay, so this is one thing that came from Google, which says the translation model and then vertically translation quality. So the quality is kind of compared with human and neural GNMT and phrase-based PBMT. So if you see here, the perfect translation goes here as 6. So we have scored between English to Spanish, English to French, English to Chinese, Spanish to English, French to English, and Chinese to English. So mostly English to Spanish is doing better over other, but however it doesn't still meet this range, right? So that is kind of a lot of improvement that has to be done, and I would like to cover more about those aspects in my later sessions. But this is a kind of a brief idea of how machine translation from the past improved over SMT and NMT, and the progress of these translation techniques over time. Okay, so I thank you with this session. Any questions? Okay, so there are no questions so far. With that, I will hand it over to